if I have time, I would like to show you one example. Okay, we still have time to show you one example. This example, okay, again, for the rectangular cross-section, okay, for rectangular cross-section, we know the second moment, okay, because as a symmetric, section is symmetric, so in this case, the equal area axis is the same as the neutral axis. So don't need to distinguish between the neutral axis and the equal area axis, okay? And the distance between the neutral axis to the outmost edge is equal to h/2, okay? So we can obtain the elastic section modulus, okay? And how about the plastic section modulus? You just need to consider two regions of section, okay? And for each region, the area is equal to total area over 2. And y1 is equal to y2. It means the distance between the centroid of each subregion to the equal area axis. So it is equal to h/4. So we can obtain the plastic modulus, and the ratio is equal to shift factor. Okay, shift factor. And here is a more difficult example. We consider T section. Maybe I will put a similar question in the final examination, how to calculate the plastic modulus for cross-section like this one. Okay, so it is very difficult to calculate the elastic modulus. So if you feel difficult to understand, just forget it. Okay. Just ignore it. Okay, mainly I show you how to calculate the plastic modulus. Okay, but in my solution, I provide you the solution for both elastic modulus and the plastic modulus. Okay, if you want to obtain the elastic modulus, you have to find the neutral axis location. We don't know the neutral axis. Okay, and if you want to obtain the plastic modulus, you have to define the equal area axis. Okay, so we have two axes. So this is a formula. Okay, how to define the location? We assume the distance between the top of the section to the location of the neutral axis is y bar, and the y bar is obtained based on the formula given here. Okay, you can divide the section into any number of subregions. For example, here we consider two subregions. Okay, so for each subregion, we can obtain this total area. And then we use this formula given here. Okay, we obtain the area of each subregion times the distance between the centroid of the subregion to the location of the neutral axis. So Z bar is defined with respect to the equal area as a neutral axis. To neutral axis. So we can obtain the location of the neutral axis, and then we can calculate the second moment. The second moment should be obtained based on the parallel axis formula, because we have to first obtain the second moment about the centroid of each subregion, and then we use the parallel formula to obtain the second moment about the neutral axis. Okay, neutral axis. After obtaining the second moment, we can obtain the elastic modulus. Elastic modulus, according to the formula given here, is equal to I/C. But please understand, we have two values about C. C means the distance between the neutral axis location to the outmost edge of the section. We have two outmost edges. One is the top of the section, the other one is the bottom of the section, right? So C means two distance. One is the distance from the neutral axis to the top of the section. The second one is the distance between the neutral axis to the bottom of the section. You just need to select the larger value. Okay, you just need to select the larger value to calculate. So here, because y bar is equal to 29. Okay, so 29 is less than 100 minus 29. So we use 100 minus 29. Okay, because this is a larger value. Okay, this is a larger value. So we can obtain the elastic modulus. Okay, I just show you the solution. But now we focus on how to determine the plastic section modulus. Okay. If you want to obtain the plastic modulus, you have to first define the new equal area axis. So please ignore the neutral axis. Okay, please ignore the neutral axis. Okay, and the equal area axis. Okay, divide the whole cross section into two equal areas. So the definition is very simple. Okay, but why I would like to put the same question in the final examination, because you have to make a judgment. We don't know the location of the equal area axis. Okay, it may be within the flange, and also it may be at the web. Okay, the web. Okay, so you can have two approaches. I just show you the first approach. Okay, the first approach is trial and error. Okay, you can first assume the equal area axis is within the flange. Okay, is within the flange. If it is within the flange, okay, the flange will be divided into A1, A2. Okay, so if the equal area axis is within the flange, A1 should be equal to A2 plus A3. Okay, A1 plus A2 and plus A1 is equal to A2 plus A3. So it's very simple. You calculate A1. A1 is a function about H. Okay, so A2 is equal to, okay, it's also a function about H, because total total depth of the flange is equal to 12.5. So 12.5 minus H times 100 is A2. So A1 is equal to A2 plus A3. So firstly, we assume the equal area axis is within the flange, and then we use this formula. Okay, we use this formula to calculate the plus modulus. Okay, so if the equal area axis is within the flange, A1 is equal to A2 plus A3, so we can obtain H value. Okay, but after obtaining the H value, you have to do one thing. You have to verify your assumption, because your assumption is that you assume the equal area axis is within the flange, so H must be less than 12.5. Okay, if the solution about H is less than 12.5, that means your original assumption is correct. If H is larger than 12.5, you have to make a different assumption and repeat calculation. Different assumption means you assume the equal area axis at the web. Okay, and then the web is separated into A2 and A3. And then the equation becomes A1 plus A2 equal to A3. So do you understand? Okay, so we can obtain H. After obtaining H value, you can obtain the area for A1, A2, A3, and then find the distance between the centroid of A1, A2, A3 and the location of the equal area axis. We are able to obtain the plastic modulus already. Okay, and after obtaining the elastic modulus and the plastic modulus, we can obtain the shift factor. But as I mentioned, you just need to understand how to calculate, okay, the plastic modulus. Okay, so I hope you can fully understand this example, because I tried to put this question again in the final examination. Okay, that's all. Okay.